Hey guys, we're here on lesson 3.2, which is all about exponential functions and models. All right, so the form of an exponential function. You may have seen this before. Exponential functions are written as f of x equals a times b raised to the x power. The f of x is our function notation. The a is often referred to as our principal or our y-intercept, okay? So in real world scenarios, the a is typically how much there is in the beginning, our starting amount, okay? That's very important. All right, the b for this equation is the base of the exponential expression. This will model the change that is happening when the penny is doubled every day. So what is our rate of change here? What are we multiplying by every time? And of course, the x is the variable. So when we use this with exponential properties, there's something called the power property, which basically says that if you have an exponential function with your principal amount, your rate of change, and then you're raising it to the amount of time, which is usually in our exponent. Notice how we have 7x as our exponent. We can take that 7 and move it into the parentheses now so that the 2 is being raised to the 7th power. We evaluate that. 2 to the 7th power is 128. And now we have two equivalent functions. So the function that says our penny times 2 raised to the 7x power is the same value as our penny, our 1 cent, raised to the, or times 128 raised to the x power. Those are equivalent expressions. Okay. Let me erase here. All right, some applications of exponential functions. So when do we use these? We like to use exponential functions to talk about the growth of a savings account, okay, when we're talking about money, to talk about the population growth or decay of a species. If we're talking about the decay of isotopes, those are chemical compounds, and much, much more. Have you ever heard the statements, our stock is up 4%, or prices have been slashed 25%? They aren't saying that the stock is only 4% of what it's worth before, but that it has increased 4% on top of what it already was. Now, when we're talking about these financial applications, we take our function from before, and we write it out using some financial terms. So essentially, this is the same function that we had before. Let me change out of yellow here. Let's do a nice, okay, so we had before on the previous page, f of x equals a times b raised to the x power. Well, all the pieces are the same here, but now they just look a little bit different. So the f of x is still our function notation. The p, right, is the same thing as our a before. It's still our y-intercept or our principal amount or our starting amount, what we begin with. And inside the parentheses, we have 1 plus r. The r is our rate of change, okay? It's going to be expressed as a decimal. So anytime we get a percentage rate, we want to divide it by 100 to change it to a decimal. Let's jump into some examples so you can see how it's used. All right, so Paula puts an initial $100 into her savings account. The account has 3% annual compound interest. Create a function that models her savings account. So again, our principal amount of money is $100, so we put that outside the parentheses, times 1 plus that 3%. Remember that percentage needs to get changed to a decimal. So I take the 3 and I divide it by 100 to get 0.03. And that's what I add to the 1. That is my rate of change. Okay. And now we just simplify it. Well, 1 plus 0.03 is 1.03. Okay. Then they want us to calculate the amount in the account after 5 years. Well, that is our variable, the time, and that's what we're going to raise it to. We're going to raise it to the 5th power. Then from here, this becomes a simple calculator problem. You type everything into your calculator and you get your answer. Make sure you're rounding to the nearest hundredth because we're dealing with money. All right, the graphs of exponential functions, okay, they show you if it's a growth or a decay. So if your function is growing, notice how it starts off growing kind of slow, and then it hits a point where it begins to increase very quickly. That is the typical pattern of an exponential function. If it's a decay, then your graph will start off high, and then eventually it will begin to slow all the way down. When you're looking at the functions, if your base, okay, the b or that rate, that r, is greater than 1, then your function will represent a growth. If that term is between 0 and 1, so if it's a decimal or a fraction, then your function represents a decay. Excuse me. The domain of exponential functions will be represented by all real numbers, okay? The y value or the range will depend on the situation, but it can be represented as the numbers that are greater than 0. Okay, for the y-intercepts, it's a very key important part of the exponential functions. And if you again look and compare at the 2 different ways that we are writing out the same formula, the a, the number in front of the parentheses, is the y-intercept. And when we're talking about financials, the p, the principal, is the same. It's the y-intercept. Okay, so here's just a quick example. Looking at this graph, before I even take a look at the numbers of the function, I can clearly see that this represents a growth because reading my graph from left to right, it's starting off slow and it's skyrocketing up. The domain of this function, okay, the x values, would include all real numbers. If I plug any number in for x, I should get a value out. The range, notice how this graph does not ever touch 0. It's all the numbers that are greater than 0. The y-intercept, where this crosses the y-axis, is right here at +3, or the coordinate 0, 3. All right, finding the rate of change is very similar to how we did it for linear functions or for slope. So here we go. You start out with a penny that will double every day for 30 days. Find the average rate of change from day 7 to day 14. Remember that this function has already been shown to us. Okay, so our penny is our principal, our starting amount, and it's doubling, so we have 2 raised to the x power. So our x values for the day 7 would be 7, and our x value for day 14 would be day 14. You plug those in, and these are your y values. So this is my y, and this is my y. All we're going to do is take that slope formula that we are already comfortable with, and we're going to plug these values in. So let me just move these markings here. Remember, FB and FA, that's just a fancy way of saying y2 minus y1. And B minus A is just, again, another fancy way of saying x2 minus x1. It's that regular slope formula that we're already familiar with. Once you plug in all the numbers, then you will see that your rate of change is 23.22. Okay? That means that it will increase $23.22 per day. Alrighty. Now, on eLearning, every module has practice problems. Please take a few seconds to go through, solve these problems, figure them out. Every time you answer, like I just clicked a random answer, it will give you some feedback. If I get this question wrong again, it will give me more feedback, okay? Use this to help you guide you so that you can do well on your quiz. All right, guys, good luck.